Hi, so you want a quick overview of string theory? Great, you've come to the right place. Standard model of particle physics. When we think of an atom, we generally think of a nucleus made up of protons and neutrons, surrounded by a cloud of electrons. If we look deeper into the heart of the nucleus, we realize that the protons and neutrons are made up of other particles called quarks. Quarks, like electrons, are thought to be elementary particles that make up our universe. The Standard Model categorizes all the elementary particles into either matter particles, otherwise known as fermions, or force carrier particles, otherwise known as gauge bosons. Fermions are divided into quarks and leptons. There are 6 quarks, up, down, charm, strange, top and bottom. There are 6 leptons, electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. The gauge bosons are gluons, photons, and the W and Z bosons. There are 4 forces that we know of: the strong force, the electromagnetic force, the weak force, and gravity. Gluons mediate the strong force between the quarks, holding them together within the protons and neutrons. Gluons also mediate the strong force between the protons and the neutrons, holding them together within the nucleus of the atom. Photons are particles of light which carry the electromagnetic force that holds the electrons in atoms. W and Z bosons carry the weak nuclear force, which is involved in some forms of radioactivity and plays a role in how the sun burns. The Standard Model also describes the Higgs field, which is a quantum field that permeates all of space. Particle interactions with the Higgs field imparts other particles with their mass. For example, the top quark is interacting with the Higgs field, and this is what is giving the top quark its mass. The Higgs boson is the local excitation of the Higgs field. And there's one final boson to talk about, the graviton. This is a hypothetical particle that mediates the gravitational force. What is string theory? String theory proposes that rather than the elementary particles, the fundamental building block of the universe are tiny vibrating strands of energy from which all the matter and all the forces in the universe emanate. Why string theory? The general theory of relativity and quantum mechanics are 2 of our most successful theories in physics. The general theory of relativity describes how the force of gravity works, and quantum mechanics describes how the other 3 forces work at the smallest of scales. But the 2 theories are incompatible. General relativity describes space and time as a smooth continuum, whereas quantum mechanics describes space and time as being quantized. String theory attempted to resolve the incompatibility and explain how all the 4 forces work, which made it popular, but it had a couple of issues. 1. The theory originally dealt with only bosons and did not include a description for the fermions. And 2. It predicted the existence of hypothetical faster-than-light particles, tachyons. These particles would travel back in time and destabilize space. Adding the principle of supersymmetry solved both the fermion and tachyon problem. This leads us to ask, what is supersymmetry? Supersymmetry and superstring theory. The principle of supersymmetry says that nature is symmetric, and as a consequence, every boson has a fermion superpartner and every fermion has a boson superpartner. When supersymmetry is combined with string theory, superstring theory emerges. When physicists refer to string theory, they generally mean superstring theory, which describes all the fermions and bosons as being the result of vibrating superstrings of energy. Higher dimensions. We live in a 3-dimensional world, meaning there are 3 directions we can move in: forward and backward, up and down, and left and right. Einstein added a 4th dimension, time. When describing where we are at any given time, we combine our location in space with time. So for example, if I wanted to meet my friend Janet for a coffee, There is no point in telling her I'll meet her outside Covent Garden Station if I don't also give her a specific time of when I will be there. Einstein combined the 3 dimensions of space and the 1 dimension of time and termed it space-time. In the theory of general relativity, space-time is described as the fabric of our cosmos. String theory proposes the existence of additional spatial dimensions plus the 3 familiar ones we experience in our everyday lives. In fact, string theory proposes 6 additional spatial dimensions that are curled up or compactified around every point in our 3-dimensional space. We can't experience them as these higher dimensions are so small we don't have access to them, but superstrings do. These superstrings oscillate in these dimensions in vibrating patterns that go on to create the matter and forces in the universe we see around us today. M-theory. String theory was a popular area for study owing to the elegance of its mathematics and the fact that it appeared to be a theory of everything. But there existed 5 versions of it. M-theory illustrated that these 5 versions were ways of looking at a more fundamental theory. M-theory also introduced 1 additional spatial dimension, the 11th dimension. This extra dimension allows a string to stretch into sheet-like membranes, and M-theory went on to describe a hyperspace within which membranes exist with universes attached to them. These membrane or so-called brane universes make up the multiverse, and one of these branes is our very own universe. String theory answers some very big questions. 1. The weakness of gravity. Compared to the other forces in the universe, gravity is incredibly weak, and scientists have long questioned why. The weakness of gravity can be illustrated by the fact that we are able to pick up a set of keys off the ground using only a magnet. Even with the entire gravitational pull of the Earth being exerted on the set of keys, one simple magnet is able to overcome it. In fact, gravity is a staggering 10 to the power 40 times weaker than electromagnetism. String theory explains the weakness of gravity by proposing that gravity seeps off our universe and into the higher dimensions. Superstrings can be either open strings or closed strings. Open strings are attached to the branes and have no way of leaving them. Closed strings, however, are able to seep off the branes. So if we imagine gravity to be closed strings, that would explain its relative weakness in comparison to the other forces. The second thing that string theory answers is the origin of our universe, how our universe came to be. General relativity and quantum mechanics can't go back to the very beginning of time and reveal how our universe was born. The mathematics of both break down when we attempt to go back to the very beginning and starts offering up nonsensical results. String theory gives us its own unique explanation of how universes are born. They are born out of membrane collisions. How can we test string theory? We imagine that the compactified additional dimensions of space twist and turn to form a Clobbeau shape. It is supposed that the particular geometry of our Clobbeau shape allows strings to vibrate and oscillate to give us the exact requirements for our universe to have formed. So in essence, it is because of our Clobbeau shape that the mass of the elementary particles and the strength of the different forces are what they are. If we were to know the exact Clobbeau shape of our universe, we should be able to work backward and calculate the exact masses of the different particles and the strengths of the different forces, thus proving string theory in a roundabout way. But the Clobbeau shape could have many variations, which would create many different string vibrations and oscillations, giving rise to many different types of universes, not just our own. This once again hints at the existence of a multiverse. We can test string theory in a more practical way by particle collisions. Particle collisions allow all sorts of extraordinary particles to be released, and string theory believes that these collisions could generate the elusive graviton. If string theory is right about gravity seeping off our membrane universe into higher dimensions, these collisions should show that the amount of energy after the collisions are less than the amount of energy before the collisions, as gravitons have seeped into higher dimensions. But before we get too excited, we have to note that because gravitons are so weak, a detector with the mass of Jupiter and 100% efficiency placed in close orbit around a neutron star would only be expected to observe one graviton every 10 years, even under the most favourable conditions. And so that, in a nutshell, is our guide to string theory. As always, we hope you enjoyed this video, and don't forget to subscribe to London City Girl for more videos like this. If you liked our content and want to help us make more science and educational videos for YouTube, please consider becoming a supporter of London City Girl Knowledge on Patreon. Patreon is a crowdfunding platform where you can support your favourite online creators by giving them a small sum of money every month. In return, you will get rewards such as graphics and wallpapers for your phone and computer, educational cheat sheets which you can print off and keep, as well as ebooks on a range of educational topics.